Hello and good evening. Today I want to talk about those little RF power monitors that you can find sometimes on eBay or online for fairly little money. And as you can see, those units are labeled with frequencies from 1930 to 990 megahertz. They are made for cellular infrastructure equipment, aka base stations, and basically what they're used for is they are in the feed line and monitoring the forward and reflected power. And if for some reason the output power drops, or if there's a mismatch because of a damaged feed line or something like this, then it triggers a alarm and notifies the operator to dispatch a technician to the cellular site to get things fixed. So usually I stay away from things that are specifically designed for cellular bands, because usually the stuff is narrow band and you can't really use it easily for any other frequency bands, like for amateur radio or other commercial frequencies. But in this case I pretty much got those parts for free. They came in a surplus lot with some other stuff I bought, and they've been sitting around the lab for a while, and now I finally figured out, okay, let's play with them and see what they are really, if they're good for anything else but for its original intended purpose, and if not, then well, at least see if the connectors can be salvaged to use for something else, because they're nice little stainless steel SMA connectors, and maybe you could use them for something, for other purposes, reuse them. So this whole thing is actually fairly easy constructed. As you can see on the sides, you got a little MCX connector for the coupled output, and you have a SMA connector. So the MCX is for the coupled output. Note that those things do not have built-in detectors. It's an RF output, and as we can see, this whole thing is constructed as a strip line coupler. It's not a microstrip, and they seem to have used from the color of the substrate. It doesn't seem to be FR4, but rather some kind of a Teflon material, Arlon or something like this, potentially because of power handling, because the power levels on cellular infrastructure equipment can be in the 100 of watts range. So this thing, of course, has to be able to sustain those power levels. And of course, since this is not a piece of test and measurement equipment, but rather stays permanently in the signal path, it also has to be low loss, which could be another explanation for using Teflon based materials. So at first I got curious and say, okay, well, let's take a look under the hood of this thing. So since I have quite a few of them, I decided to pry one open and just take a look inside. So as we can see, it's a strip line part. I took off the bottom, so this one right here is the piece of Teflon for the top part of the strip line, and since this one is the bottom part, so it's a fairly straightforward design. It's basically a dual directional coupler, and you see two 50 ohm resistors, one terminating the forward, one terminating the reverse path. So it's kind of hard to tell what the power rating is on those resistors, but I would guess probably about somewhere in the 2 to 5 watt range, because they are not cooled or something. So it's definitely not a high power thing. There are some thermal vias under the resistors, obviously to remove the heat from the part, which is a quite common practice. And so this thing has a couple of discolorations down here because obviously it's been exposed at some point in time to moisture. So as you can see, it's not rocket science. It's just regular RF engineering, and so kind of the length of the transmission lines kind of gives you an idea about the frequency range. But there are no special. It's not a multi-section coupler or something, so it's not. It doesn't. It suggests it's not a wideband design per se. So let's measure one of them and just see how this thing, as a measured performance, actually looks like. So I got my network analyzer cranked up right now, and I just calibrated for through line for S21. Set my frequency to 400 megahertz to 6 gigahertz, and I got my test port power set at 5 dBm. So this thing is calibrated, as you can see. So now let's connect the device on the test and measure the performance. So let's start with the forward path, and for stability reasons I got this clamped in a drill press vise. It might look a little bit crude to some people, but it works. It keeps the units from flapping around on the lab bench. And so I got a little MCX to SMA cable right here. I got my test port 1 connected to the input, got the output terminated with a 50 ohm termination, and of course I got my little friend here, a little torque wrench, make sure that everything is torqued up with the right torque for SMA, 5 inch-pounds or 5 foot-pounds, sorry. And so now let's look at the network analyzer. So this thing actually looks a lot nicer than I would expect it for a simple single stage coupler, single section coupler to look. So down at the high end at 5.7 gigahertz we got about 28 dB coupling, and so that corresponds with the 6 centimeter band. And then let's go to 3.4 gigahertz, which is basically the 9 centimeter band. So at 9 centimeter we got about 31 dB coupling, and then at 13 centimeter we still got 31, and down at 1.3 gigahertz it actually also is about 31. So it's actually pretty nice performance from all the way from 23 centimeters up to in the 6 centimeter range. And then of course you see this dip down here, so don't expect this thing to work at higher frequencies. So now let's look at the reverse channel. So this is right now with the output connector being open, so there's nothing connected, no termination, and the loss of the reverse output, it's about 32 to 36 dB, so it's pretty close to what the forward channel is. And so now let's connect a 50 ohm termination. There you go. The output is terminated now with 50 ohms. So it's not a precision termination, it's just a regular general purpose 50 ohm in-mid termination, nothing fancy. And as we can see, we are in the 61 dB loss coupling, and it's the high end. It's 5.7 gigahertz. We are only at 32, so the performance for 5.7 gigahertz is not all that great, as we can see. For the reverse channel, obviously the directivity is not really all that nice, but we still get fairly good performance up to about 4 gigahertz. So yeah, you can use this thing for amateur radio bands up to like about 3.4 gigahertz. If you just want to measure or monitor forward powers, then you can use it all the way up to 5.7. So this now is the insertion loss, and we are getting about 0.5 dB at 1.3 gigahertz. We're getting about 0.8 up at 4 gigahertz. And so let's change this marker here. And if we go up all the way to 5.7, it's actually, let's see, average run. Okay. About 0.5 dB. So yeah, I mean, like I said, it's a fairly simple design, and you really don't expect any high performance out of it, but it will work okay for amateur radio bands. So that's it for tonight. Thank you for watching. Please don't forget to like my video and follow me for future posts on other RF related subjects.